Hello, I'm Robert Raussendorf. Welcome to my website. I'm a physicist and quantum information scientist. I work on the theory and on the foundations of quantum computation. In this short video, I want to give you a glimpse into the questions that I ask and the phenomena that I study. So, come in. Let's begin here. About 50,000 years ago, humans figured out how to count. Their concept of number was very simple at the beginning, like 1, 2, 3, many. But over time, it evolved into rings and number fields. Numbers can be operated with. They can be added and multiplied, and if you choose the right kind of numbers, also divided by one another. Fairly recently, on our 50,000-year timescale, the notion of algorithm was invented. And in its wake came mechanized computation. The computing device I have sitting here on my lap is really rather impressive. High-resolution graphics, bright colors, a computer algebra system running. It persuades me to proclaim that we have cleared level 1 of the computation game. And now we stand at the entry point of level 2. We are no longer looking at our fingers for inspiration, but instead at the Schrödinger equation and the Born rule. Welcome to quantum. In a way, we are in a very similar position to those earlier humans that started level 1 50,000 years ago. With a few notable exceptions, such as Shor's factoring algorithm, our understanding of the landscape we just entered is very limited. This brings us to the question that I ask in my research work. How can we harness the quantum for computation? And how do you even ask this question? While nature is all around us, she has no email or telephone number, so we can't just call. A strategy in science is to narrow down the question, to pick a particular aspect to focus on, to form a hypothesis and see where it leads. If this provides us with snapshots, the bigger picture is then reconstructed from them. Here I tell you about 3 avenues along which we inquire in my research group. We focus on symmetry, algebraic structure, and computational resources. Computational phases of quantum matter. So that's the part about symmetry. In some models of quantum computation, such as measurement-based quantum computation, the viability of computing solely hinges on the presence of a suitable symmetry. The scheme of quantum computation uses a highly entangled quantum state as a computational resource. Further, as we have only recently learned, when this state is continuously varied while preserving the symmetry, the computational power remains unchanged. So, symmetry clearly plays an important role. And this leads us to the following question. Can schemes of quantum computation be classified by symmetry similar to, say, elementary particles? And if this is so, is the same true for quantum algorithms? And if that were true, could it help us construct new quantum algorithms? Putting paradoxes to work. What you see here 3 ways is Merriman's star. Let me give you just a tiny bit of background on it and what it is used for in quantum physics. This begins with a paper written by Einstein, Podolsky, and Rosen in 1935, entitled Can Quantum Mechanical Description of Physical Reality be Considered Complete? Einstein was uncomfortable with the prediction of quantum mechanics that the state of a quantum system could be affected at an instance by a measurement far away. Say that the measurement of a particle on Earth could without delay affect the quantum state of another particle on the Moon. He called this property of quantum mechanics spooky action at a distance. Einstein cast his discomfort into a scientific argument. He and his co-authors showed, or so they thought, that quantum mechanics must be incomplete. They didn't say that quantum mechanics was wrong, only incomplete. That is, given certain innocent-looking assumptions, they showed that not everything that can in principle be predicted can also be predicted by the theory of quantum mechanics. How do we physicists respond to that conclusion today? I would say that most of us accept the argument, but not the assumptions. The weirdness of quantum mechanics has become easier to accept in the intervening 85 years. The reason I mention the EPR paper here is its concluding paragraph. The authors observe, and I now quote, "While we have thus shown that the wave function does not provide a complete description of the physical reality, we left open the question of whether or not such a description exists. We believe, however, that such a theory is possible." End of quote. This is the cradle of non-contextual hidden variable models. Such models try to describe quantum mechanics in the terminology of classical physics, specifically classical statistical mechanics. In those models, all measurable observables have predetermined outcomes, and those outcomes are merely revealed when the measurement happens. By the way, this is precisely how we think about measurement in the world around us. But measurement, according to quantum theory, works differently. It's a process, and it's an irreversible one. So Einstein, Podolsky, and Rosen believed that hidden variable descriptions of physical reality are viable. So are they? The answer turns out to be no. This was shown in two distinct ways. John Bell came up with an inequality that distinguished between the predictions of quantum mechanics and the predictions of all local hidden variable models. The experiment was performed and decided in favor of quantum mechanics. The second way in which those hidden variable models were ruled out was by pointing out their necessary internal inconsistency. This is the content of the Cauchy-Specker theorem. And now, finally, we have arrived at Mermin's star. Mermin's star is the basis for one of the simplest proofs of the Cauchy-Specker theorem. Not one of the first, but one of the simplest. It is an arrangement of 10 quantum mechanical observables, 6 local and 4 non-local, that satisfy certain algebraic constraints. They are very carefully chosen. You cannot stick arbitrary observables in their place. Now, a funny thing about Mermin's star is this. It can be repurposed as a very simple quantum computation. This connection was first realized by Janet Anders and Dan Brown from University College London. It represents the trailhead for the exploration of quantum computation from the perspective of the Cauchy-Specker contextuality. And it is the reason for the title of this slide, Putting Paradoxes to Work. To summarize the main point, in Mermin's star and all its relatives, we are dealing with a certain algebraic structure. And we observe. If you add the assumption of a hidden variable model on top of this structure, then you get a contradiction. But if you don't, then you get a computation, a quantum computation. And so we are led to ask, what precisely is this underlying algebraic structure? We have investigated this question in far greater generality than shown here for Mermin's star. And our answer is cohomology. Cohomology is a notion of algebraic topology. It characterizes features of geometric objects that remain invariant under continuous deformation. A final comment about this slide. So far, we have discussed Mermin's star with and without the assumption of a hidden variable model. This corresponds to the image on the left and in the center, respectively. On the right, Mermin's star, along with its sibling, Mermin's square, are shown as little monsters. What this is about, we'll see on the next slide. So this brings us to the final glimpse that I'm going to discuss here. Quantum computational resources. We ask, which property of quantum mechanics is responsible for the quantum speedup? Once identified, can we treat this property as a commodity, a resource? So here is a candidate for such a property, the negativity of Wigner functions. Wigner functions were invented pretty much around the same time as the EPR argument, and by now too have percolated to the field of quantum computation. But let me cut the story short this time. The Wigner function is a particular representation of the quantum state. It contains exactly the same information as a density matrix. This particular representation is real valued for all quantum states, and significance is attributed to negative values. Namely, those negative values are seen as an indicator of quantumness. The intuition comes from quantum optics, the home turf of Wigner functions. But in quantum computation, there is a precise connection between the negativity of Wigner functions and quantum speedup. In the model of quantum computation with magic states, a quantum speedup can exist only if the Wigner function of the initial state has a lot of negativity in it. That is, it is substantially negative in a large number of places. The negativity of Wigner functions is a precondition for speedup. You need it, but if you have it, that's not a guarantee for anything. That's why we can't call Wigner function negativity a resource yet. And there's more trouble. In what I have explained so far, I have shuffled an important distinction under the rug. The distinction between odd and even Hilbert space dimension. If the local Hilbert space dimension is odd, then what I just said goes through smoothly. But if the local Hilbert space dimension is even, as is prominently the case with qubits, then all hell breaks loose. As it turns out, to blame are Mermin's square and star and their fellow little monsters. In my research group, we have recently resolved the case of multi-qubit systems, if you are willing to accept that one and the same quantum state can be described by multiple Wigner functions. And if you do, then there's a surprise in store. So for the not so faint of heart, I recommend the paper that is listed here at the bottom of the slide. I have given you a few glimpses into my research work, but there is of course more to explore. I work, for example, on measurement-based quantum computation, a scheme of quantum computation I have invented jointly with Hans Briegel. I also work on fault-tolerant quantum computation, which is about keeping the quantum speedup in the presence of decoherence. About all these directions, and of course about what you have heard here in this video, you can find out more when exploring my website. So, have fun and thank you for watching.